to be here to share with you one of the most intriguing scientific questions we concur these days, and it is how life started on Earth. But I don't want to do it in this way. I like to do that with the question, why can't we make life in a laboratory? And why is that so important is obviously the next question you ask yourself. And I will show you that that is necessary and required to survive on Earth through the decades to come. But before going to that question, you can ask yourself, what is actually life? We have to define life. What is that and what is life? Suppose an alien comes from outer space to Earth and have to report back home to say what is life on Earth. And that is not that easy to tell in words. If something moves, is that alive? No, we know cars are not alive. If it's out of molecules, alive? No, certainly not, because sugar is not alive. But we all know if we look through this, what are the parts that are alive? Some of you probably think the virus is alive, but they're wrong, they're not alive. So it's difficult to define. But since the beginning of this century, scientists all agreed more or less on a definition of life. They've come up with the 7 pillars of life. And obviously I don't have the time to go through all of these 7 pillars today. But it makes sure there's a program. And the program, in our case, is DNA. And that is improvised, and it will be changed. We are compartments. And very importantly, life is always out of equilibrium. It uses energy. So if you listen to the radio or television and they tell you, be in balance, be careful, because as soon as you're in equilibrium, you're dead. You have to be moving around by energy. And obviously, you have to regenerate yourself and further the other things. I don't want to go into all of these details. But now, knowing this, it's obvious that the smallest piece that is alive is the cell, the building block of life. So the question I raised in the beginning is not how we can make a dog or how we can make one of us. The question is, why can't we make a cell in a laboratory? Now, in order to figure out what a cell is, I think it's good to see for a minute what it means, how large it is. We stay with the universe and we make steps and making them smaller and smaller and go to our solar system, and we start at 10 power 26 meters, and in the meantime we're in Europe and we're now at millions of meters. We zoom in the Eindhoven region, in which we come into the kilometers, and we zoom into the strip, and if everything works out well, we zoom somewhere in where we are here today. We're now in the meters, we're in the public, but we're not ready yet. We continue to go into the heart, and we continuously make steps. 100, 1,000. Now we're in the cell nucleus. Now we're in the chromosome. We're still not ready yet. We're 10 minus 9 meters into the DNA of the molecules, which are atoms. But atoms are protons and neutrons. And if you're in a proton, you can continue to zoom in quarks and electrons, and at the end, you come up with the smallest distance we know in science. That's Planck's distance. And if you've seen, we have made 10 to the power 60 meters of steps, from the largest parts we know to the smallest part we know on Earth. And if you take that into, I hope it works. Oh, here it goes. If you look to it, the cell is just in the middle. Is that coincidence, or is that just the limitations of our brain? Probably it's the last one, but we don't know. At the same time, I see what you see over here. I also put in the thing of complexity. Complexity is not the reverse of simple. That's complicated. Complexity is something in which you don't understand the properties based on very small parts that you understand, due to the fact that they're all working together into a system and into a network that we don't understand. And that's remarkable that we don't know it. And we don't know enough about a cell. And maybe one of the most important parts of that is that the cell is too big for the natural laws of quantum mechanics. But on the other hand, they're too small to be described by gravity or relativity theory. So we don't have a real theory to understand the parts of the cell. But in the meantime, we know a lot about the cell. The inner life of the cell is known to many of us. I think we know now 2% of the cell, and 98% we don't know of it. And on the other hand, it's important to figure out how and what. And if it works. So this is the cell. We know only about 2%. And the question is now, why is it so important to make life? Life is based on molecules. Life is making our molecules. Life, through all of the 3.5 billion years of the existence of life on Earth, made available the molecules we're dealing on today. And we're sitting on molecules, we're using molecules, that's all what it is. But the world is changing. And if it's the next, and the next, we will see we're using with enormous amount of people, more and more cities, and more things we're using. And what you see, that is a way we can't continue because we're using up all of the natural systems for the way we do. That was built up in many, many years we're using for oil. And what we do today, we do for feed and food. So the question is, if there is not natural biology that can do the job for us, then we have to make artificial life to do it exactly the same way what nature did for us so many, many billions of years on the earth in order to live here in the year 2100 or something like this. So it's my belief that we have to come up with strategies to make artificial life in a laboratory. Now, according to the scientists, we know a little bit about that whole procedure of going from quarks and atoms to molecules, from molecules to cells, from cells to tissue, organs, and animals. And you can divide it into 3 areas. Chemistry and physics have taken care of atoms and molecules. And chemists are now able to make every molecule that exists on Earth to make in a laboratory. Every molecule is possible, provided you have the money, you have the time. On the other hand, biology knows if you have a certain cell, that you can do things with a cell. Of a stem cell, you can make organs, and maybe we'll hear more about this during this evening. The most critical part in that whole strategy from atoms to life is how to go from molecules to a cell. An area that is extremely difficult to conquer. And I will show you where scientists today are working in order to do so. And everything works out, it's on this slide. There are 2 ways to figure out how to make life. And it's comparable to how you make, for instance, a motor car. Some people buy a motor, disassemble it, and then make it again. Some others try to make it just out of water, air, clay, iron. These are the 2 approaches here as well. The first one, what is called molecular biology or synthetic biology, is the disassembly and assembly of cells. So taking parts out and putting them in again. The other approach is building it up from scratch. I'd like to share with you what is done at the moment in science to close this gap. Let's start with the biology. Obviously, that starts with the program and the beautiful invention by Watson and Crick about a double helix of DNA. And the program is written with 4 letters in base pairing. And if you take a number of these letters, you make a gene. And the gene encodes for a protein. And the protein helps to make all of the molecules. And with that, people will able to change the DNA, to add a gene to a species, for instance to corn, and make the corn more resistant to all kinds of diseases. It's only for that reason that so many people can eat on this earth. But also with this methodology, they make drugs that you use today. It's by the genetic modification. The next step is really to take out all of the DNA out of the most simplistic cell. It is done by the Greg Venter Institute They synthesize in the laboratory a DNA with 1 million base pairs out of oil. Bring that back into the cell. And that cell works as a laboratory cell. So really, it brings a cell. You disassemble, you take all of the program out, you put new program in, and it does what it does. And you can't believe that the ExxonMobil company gave $750 million to that institute in order to play around with the algae, to get out all of the stuff that is not needed to be alive, and to bring everything in that produces oil. That's how far we are in the area of bringing that cell down to its most simple form. What is going on from the other side? That is, how can we build it up from scratch? We have to synthesize molecules, and then we have to assemble the molecules into something that is a cell. We don't want to make the cell that is the cell that you have in a bacteria or in a human being. We want to make something completely artificial that only does what we want to do. For that we have to synthesize molecules that are based on simple atoms. 98% of all of life is made of these 5 very simple atoms. And we can make all molecules out of it. And the molecules are the building blocks of life. Not only because they're the basis of the cell, but also that cell makes molecules that chemists and biologists turn into molecules that you live on. Materials, fuel, healthcare, drugs, food, feed, whatever you... Without molecules we do nothing. It all comes out of biology, life, which are molecules itself. And the only thing that comes in is the energy from the sun. That brings it into molecules and energy of molecules, and that energy and molecules are written back by us. And the only thing what we do is produce waste. Entropy of waste. And what we ask from nature to bring the waste all the way back to useful molecules. And that we have to stop. Next, I told you we can make every molecule on Earth. Not me personally, but our society of chemists can synthesize every molecule. And suppose this would be a laboratory. And I tell you exactly which molecules are in the cell. And I also tell you which ratio they're in the cell. And I put them all here in this laboratory. The only thing I ask our chairman, just please self-assemble for me a cell. Now scientists never say never. But I'm sure if you just bring them together and you shake, there will be no life, no cell. That's the difficulty. The mystery within science is how to bring these molecules together. And why is it then so difficult? It was already the Dutch scientist van der Waals who taught us everything about intermolecular interactions. And we understand something of water. It is so difficult because it's not a simple one-to-one interaction, but are billions and billions of weak interactions that work together in a dynamic, in functional object. When I do all of this here, I work my way out with all these small changes of molecules together. If the interactions are too strong, I fell here on the ground because I'm dead. It has to be dynamic. If it's too weak, I'm water. And if I do this, you see what my muscle have to do? Continuously controlling all of these weak interactions in a complex structure. Now, scientists are making huge steps in this area. The next coming 10 to 20 years, you will see enormous changes in electronics, in healthcare, in drugs, in food, all based because we can make complex systems by all kinds of assembly processes. In equilibrium, out of equilibrium, continuously adding energy to it. We make enormous steps. It will take time to make a function like something that is a cell. I don't think any one of us will be on this earth when scientists are able to do it. But the first steps, you will see. Also, we in Eindhoven are doing a lot in this area. We're mimicking parts of our biological membranes of a kidney. We're making transporting polymer chains in which molecules can walk around. We can shift around with electrons, we can shift around with small molecules. We make steps in this area of science that is now so profoundly there in the scientific arena. And hopefully once, it comes, once, yeah, there it is. At one time, by bringing all of these scientists together, biologists, chemists, molecular scientists, engineers to make building blocks and bricks, and people from mathematics and models, if these three areas of science would come together, I'm sure that we come to compartments of systems that are so unique that they can transform one molecule into another. They can produce the things we like to produce. And then, hopefully, next. Yeah. I have a dream. The dream is the following. With the 10 billion of people in the year 2020 on this earth, we have used everything that is available, which is grown today and was grown millions and millions of years ago, which is now coal and oil. And we're producing continuously energy, waste, entropy. And nature at that time will be not enough to grow everything on a day-to-day basis what we use. That means we as scientists and engineers have to come up with artificial life that makes it faster to come in a complete recycling regime by what we use and what we need. And that really goes into a circle by which we hope that we can continue to live with that 10 billion people on this earth, because this earth is too small for all of us to live the way we're living here in this lecture room. And then we hope that biology on the one hand, molecular sciences on the other hand, somewhere will create the most simplest form of life. Not to create new creatures, but to make functional objects that can be used by the next generation. And I hope you will sponsor this type of research with your tax money as long as possible. Thank you very much.